Our paper tries to understand what is biological organization using a mathematical framework based on category theory and some notions called closure, that means the self-fabrication of living systems. The real mystery of living systems is that they are made by thousands of coupled biochemical reactions, and somehow these biochemical reactions auto-construct the same network that create this chemical reaction. This is closure. We're interested in this topic of self-fabrication because since 1972, more or less, Humberto Maturana and Francisco Varela created one of the most sensible theories about biological organization centered on the fact of self-fabrication. And as we feel that this is a very powerful intuition that they had in 1972, we want to explore mathematical models and to obtain a framework in order to be able to talk about self-fabrication. Another important name in this history of self-fabrication is Robert Rosen. He was a mathematical biologist, initially at the University of Chicago, and then he arrived also at the theory of self-fabrication based amazingly in the theory of categories, and in a work that anteceded the work of Maturana and Varela for a good 10 years. But his work was always shrouded in obscurity, and it was very difficult to understand. And his theory is the theory of MR system, and it's good to mention that he existed. And then it's important then to note that the theory of category has had at least a presence, not a universal presence, in the theory of biological organization at least since 1958. Here you see photographs of the three culprits of these ideas: Robert Rosen, Humberto Maturana, and Francisco Varela, who were more or less born at the same time, but they have very different academic life. And Rosen tried to use the theory of category really in a heavy way to understand biological organization. The central idea of closure is that every metabolic network is a set of processes that make components, like molecules, and these components are essential to make the process that makes them in the first time. This is the idea of autopoiesis, where the living organization is a network of processes that produce components that produce the processes that produce them in the first time. Then the basic fact is that any chemical reaction is a transformation of substances into some other substances, but in biology, in the biological network, these transformations are always catalyzed by an external molecules that makes them possible. If the molecule E is not present, the reaction doesn't occur. Then we want to use the theory of category to produce a theory of biochemical networks with closure. Also, eventually, we want to generalize our discovery of this self-referential equation that we call the Ouroboros equations, that we think are essential to understand metabolism. Here we have a toy metabolism made by three reactions, and here the reactions are specified without specifying the catalyzer, only the transformation of the molecules. And as you can see, this specification is incomplete. It is crucial to specify which catalyzer helps which reaction. Here you see the same metabolic network, but with two different assignments for catalysts. Then they're different processes and they have different properties. Here you have this toy example, and we have specified for the catalyzer the specific mechanism, the sub-steps by which the catalyzer makes his modulating action on top of the process. Then this mechanism is very important. Then every process can be viewed at three different levels or granularities of precision. In the first level, you only see the transformation. In the second level, you see the transformation and you specify which is the molecule responsible for the change, and in the third level, you specify the mechanism by which the catalysis. In a biochemical system, you should speak of two types of arrows. The direct arrows that represent directly a chemical reaction, and also trans arrows that represent the concatenation of biochemical reaction. Thus, they also represent some generic or functional reaction that should be taken into account. Then, the type of arrows that you have, it's really very finite, and they can be classified of how many inputs and outputs they have. And we have represented here the types that represent 99% of all biochemical reactions. And then to every arrow, direct arrow, you can assign a type. Then you can concatenate this direct arrow to produce the trans arrow, and sometimes you need to concatenate two arrows to produce a new arrow. Then this is a breaking point with respect to traditional category theory, that you need two arrows in order to concatenate and generate the third arrow. In a metabolic category, you have two types of arrows. One represents the transformation, but the other represents the catalytic effect of some molecules on some given processes. And these are very, very important, because what the central part of biochemical system is that they are close to catalysis. All the catalytics are produced by the system. I apologize that we repeat ourselves, but in our categories, you have two types of arrows. The arrow that represent transformation and the arrow that represent catalysis. And these are very, very important, because the catalytic effect is produced by the end point of some transformation. Thus, now we can apply our concept of types of arrows, from products and also catalysis to our toy metabolism. And here you have one assignment possible. Catalyst components participate in the reaction not of a mysterious action at a distance, but because they participate in a cycle of chemical reactions that produce the new elements and regenerated them. And here we have an example of this zoom in of the action of these catalysts. Thus now we can ask ourselves the question of regeneration, because if the catalysts regenerate themselves by participating in fast chemical reaction, we have the question, which products can regenerate the network itself completely? And here we're going to analyze this problem. Then now we can ask which products of the reactions are able to regenerate the network starting from themselves and from the products that are given by the environment, like S, T, and U. And by example, the single chemical STU regenerates the complete network. Also, the combination of ST and STU regenerate the network. Then these ideas can be applied to any other toy metabolism, at least. Here we have an example where you have many more reactions, and we have depicted the elementary reactions, the coupling of this elementary reaction, as well as the arrow that reflect catalysis. Yeah. Then, in this sense, this is what we call like a metabolic categories, where we can distinguish between the arrows and concatenate arrows in the way that we have explained. Many of the ideas that we have presented here are similar to the ideas that you can find in Petri nets and the work of Hordix and Steele, and recently in the work of Dmitry Luchko. As we have explained, many of the ideas that we are presenting here are similar to ideas that have been explored by others in the last 2 decades. And also, we should never forget that initially Robert Rosen in 1958, he spoke about the necessity of using category theory to understand living systems. Now, the real reality is that to understand the metabolism of living system is a job that is still in its infancy. We don't understand the robustness of living metabolism, neither the stability. Then these are aspects that surely we'll have to mix aspects from an algebraic viewpoint, like theoretical from category theory, and from dynamical systems. And some of the work that have been presented here in these symposiums are very interesting because they open some ways that biologists that like math, that is my case, we can follow and explore. Then thank you very much for a very interesting meeting.